Welcome everyone to the second lecture on convolutional neural networks. Let's start with a short recap of the previous lecture. So we started by introducing the concept of convolution. This old concept that comes from signal processing and that has been so powerful for developing deep architectures for computer vision applications. So in this case, we see two examples of what the convolution operation would deliver in the case that we have, for example, two box functions being convolved with each other and outputting this green signal here, or what would the convolution of two Gaussians look like, which in this case is, as a result, another Gaussian, which is indicated also by the green curve. So what we are showing here in the animation is the application of a filter, which is the blue signal, to a function, which is the red signal. Now, in the case of discrete convolutions, right? So that was for the continuous case. In the case of images, we usually work in the discrete domain. So we first had a look at 1D convolutions in the discrete domain. And we discussed how the filter slides through the discrete signal, how the output is computed by aggregating these values by essentially multiplying the filter weight by the signal weight and then summing up all the results. And also, what can we do when we actually place the filter on the boundary? And as we can see here, in this case, there is actually one value missing that we need to sort of decide in order to have a full-sized output. So in boundaries, we have two choices. We can either shrink the output every time we apply the convolution, the output is shrinked, or we can pad the original signals with 0 so that then we can keep the size of the input also in the output signal. So then we move to the interesting operation, which is convolutions on images. And we saw how convolutions are applied, how we have our two-dimensional filters, two-dimensional kernels. In this case, we have a 3x3 kernel that we are applying on top of an image. And we saw how this 3x3 kernel applied to a 5x5 image give an output of 3x3 if we don't use padding. So again, this idea that without padding, a convolution operator reduces the size of the output with respect to the input. And we also saw how to compute each of these values in the output matrix. Now then we moved on to the concept that these kernels represent. So what is the effect of a kernel that is sliding on top of the image? And we saw that different kernels can give us different effects on the images. For example, with a box mean filter, we can blur the image. With an edge detection filter, we can obtain these kinds of output where we have all the edges of an object detected, right? These are salient regions for this edge filter. And therefore, we can now imagine a neural network that is being trained, and therefore, all of these values here, we no longer have to handcraft them and say, I want to put a -1 everywhere and an 8 in the middle in order to have an edge detection filter. But now the neural network will decide on its own what kind of weights to put in there. So essentially what we're going to do is we're going to learn these filters. We're going to learn different operations, different filters to be applied on the image in order to extract meaningful features to do object segmentation, object detection, or image classification. We then went on to seeing how convolutions are applied on RGB images. Very, very important is that the kernel needs to have the same depth as the input. So we can see here that an RGB image has depth 3, and therefore our convolution kernel also has depth 3. Therefore, the total number of weights that our filter has is 5 multiplied by 5. This is the spatial resolution multiplied by 3 plus 1 always for the bias. And how this filter is now, we're now sliding all this filter over all the spatial locations. In this case, we have 28 by 28 spatial locations. And therefore, after the convolution of the image with our filter, we obtain as output an activation map, which is 28 by 28 by 1. So each filter gives us an activation map with depth 1. And so now, as we're building our convolution layer, what we do is we add another filter, a different set of weights, a different 5 by 5 by 3 filter, which provides us with yet another depth channel in the activation map. So essentially now with 2 filters, our activation map, our output will be 28 by 28 by 2. And this is how we create a convolution layer. If we have 5 filters, the depth at the output is going to be 5. We then discussed dimensions in convolutional layers, what dimensions are allowed, what dimensions are not allowed. We introduced the concept of stride. Therefore, how often do we slide our filter in our image? How many pixels do we skip from one position to the next? And how to compute the output based on the input size, the filter size, and the stride. We then discussed about padding, which led us to the 2 types of convolutions that we're working on. The valid convolution, which uses no padding, and therefore it's the let's say purest type of convolution in which your output size is reduced, and the same convolution in which you use the padding necessary in order to have the output size equal to the input size. And of course, the padding will depend on the filter size. Now remember how the output is computed, but also remember that in practice, the integer division is used, and you therefore have to apply the floor operator. So let's look at this example in which we have a 3 by 3 convolution with padding and being applied. So you apply this filter with stride of 2 on a 64 by 64 RGB image. So if you use the formula in order to compute the output size, you're going to have an output size of 32.5 multiplied by 32.5. In this case, we always use the floor operation in order to compute the actual output size, which is going to be 32 by 32. We then went on into discussing what does it mean, what do these filters mean as we train deeper and deeper neural nets for the task of, for example, image classification. So in this case, we train the neural network for detecting the class car in this image. And the cool thing about CNNs is that we can go ahead and look at these filters that we have been talking about. And we can see that in the low-level features, so in the first layers of a neural network, we're seeing all these low-level geometrical features emerging. So we're seeing edge detectors, all kind of edges with different orientation, with different sizes. We can see circle detection. And these are the kind of features that are going to be learned in the early layers of a neural network. Now, as we progress and as we go deeper, we start seeing what we call mid-level features. The edges coming together to form a corner, or more complex shapes which remind us, for example, of a ball or an eye. And in the deepest layers of our neural network, we're seeing the high-level features. We're seeing really parts of an object emerging from those filters, like, for example, the head of the bird here, or an eye in the case of this filter. And you see how each filter is focused on a different characteristics. And you can also imagine how then, for example, bird classification works. You put this filter of the head of the bird together with other filters that detect wings, that detect legs. And all of these together are actually allowing us to perform bird detection. And other filters allow us to perform car detection. So the nice thing about CNNs is that we can actually look at these filters and we can see whether the CNN is training properly. So visualization is also a very important tool for debugging the training of your CNN. And we looked also at the CNN prototype. So how does a typical CNN architecture look like? We saw this interlace between convolution and nonlinearities, typically ReLUs in the case of convolutional neural networks. Then the pooling operation, which reduces the spatial size. And finally, after this series of convolution nonlinearities and poolings, we have typically a fully connected layer or a series of fully connected layers that allow us to map our features to the classes that we want to classify. For example, in this case, we want to classify 5 classes. Therefore, we're going to have fully connected layers that bring down all these features into these 5 outputs. And we discussed also the pooling layer that essentially does some sort of feature aggregation. So if the convolution operation does feature extraction, the pooling layer does feature aggregation. We saw how max pooling worked and how average pooling worked. And at the end of the previous lecture, we also discussed the concept of receptive field, which is the spatial extent of the connectivity of a convolutional filter. And it is really important to have always in mind what is the receptive field at a certain layer of a convolutional neural network, so that you have an idea of how much your filters are actually seeing from the original image. So let's move on to the content of this week's lecture. We're moving on to the second part of the convolutional neural network lectures, and we're starting by looking at classic architectures. So architectures that are nowadays used for most of the tasks in computer vision. And we will start with the really early architectures. One of the first architectures, convolutional neural network architectures, that was actually used for digit recognition. And this is called LeNet, and this is because the author of this network is Yann LeCun, therefore this kind of gameplay with the name. And this was a really simple convolutional neural network, but still very much used also for kind of toy experiments with convolutional neural networks. So this architecture was initially proposed for digit recognition, in which we need to recognize a handwritten digit. Therefore, we have 10 classes. We have to classify our image into 10 classes, from 0 to 9. Now, the image is very small. The input image is just 32 by 32, and it's a grayscale image. Therefore, we have only one channel. So ideally, what we would want is we would want this particular image to be labeled, of course, as a 7. Therefore, as the 8th class, if we start with 0. So in this case, what the architecture is doing is it's applying, first of all, valid convolution. So there is no padding. So you see how the spatial resolution is reduced from 32 by 32 to 28 by 28. And so we're using here 5 by 5 kernels, and you can actually infer this by looking at how much the spatial size has been reduced. So it has been reduced by 2 pixels on each side, which means that the kernel is 5 by 5. So these are all things that you can already start seeing, and you can start getting used to the types of numbers, the type of sizes that we're usually dealing with in convolutional neural networks. So my first question for you is, given that the output of this convolutional operation is 28 by 28 by 6, I ask how many convolutional filters are there in the first layer? So pause the video, think about it, and come later for the solution. So in this case, we have already discussed that the number of filters is going to be exactly the depth of the output. So in this case, our output is 6, the depth is 6, therefore we know that we have 6 5x5 convolution filters in this first convolution layer. We then perform average pooling. Now at the time, average pooling was very much used in convolutional neural networks. Nowadays, it is very hard to see average pooling in a CNN, and max pooling is a much more common choice. And the goal of max pooling, again, is to reduce the spatial size. Note that the depth is not being changed. The depth is changed with convolution operations, but the spatial size is mostly changed with pooling operations. So in this case, we reduce the spatial size to half. And we have this 14 by 14 by 6 representation. We then apply, again, valid convolutions and average poolings. And of course, if the output has depth 16, we know that we have applied 16 convolution filters. And finally, what the architecture has at the end, in order to map this feature map of 5 by 5 by 16 into the number of classes, that is 10, that we actually need to perform digit recognition, the architecture uses 2 fully connected layers. And these fully connected layers take this input of 5 by 5 by 16 and reduce it slowly until it reaches the 10 classes as output. Now this is a common practice, because if you take the whole 5 by 16 and you reduce it directly to 10, this is too much of a reduction. It's better to go step by step and reduce it maybe first to 120, then to 84, and then to 10 classes. Now, this architecture LeNet used tanh and sigmoid activations, which are definitely not common now for CNNs. Nowadays, most CNNs use ReLU as activations. But it had this sort of main architecture design, which is very much the same as what we're using now in all architectures, which is this idea of using convolutions, then pooling, convolution pooling, and finally fully connected layer at the end in order to do the final mapping. So this type of architecture is still very much used nowadays. And again, this is the concept of doing a convolution, therefore computing a set of features, then pooling, that is performing feature selection, computing features, feature selection, computing features, feature selection. So there's this iterative process. And of course, this can get incredibly deep. In LeNet, this network was not so deep. Also, the input was smaller. But in architectures nowadays, as we will see in this lecture, this can get to really a lot of layers of convolutions and poolings. Now, also, one characteristic of these types of architectures is that as we go deeper, the width and the height, the spatial resolution is reduced, but the number of channels is increased. So you can see that we start with a 32 by 32 by 1, so a lot of spatial resolution, but just one channel. And as we reach the last layer, we had a small spatial resolution of 5 by 5, but the depth has been increased to 16. So the features extracted from the spatial coordinates are put into the depth of our activation map. And this is again a characteristic that is present in most modern CNN architectures. Now, this very tiny architecture already has 60,000 parameters. So we're training this architecture in order to find the value of around 60,000 parameters. And you will see how the number of parameters quickly grows as we go into more modern architectures. Now, the task in which neural networks broke into the field of computer vision was the task of image classification. And much of the performance came from training on a large-scale dataset, in this case, ImageNet. So you can see here some examples of ImageNet and how we get the annotations of the types of objects in the scene by having a bounding box placed around them and a label like, for example, person, dog, or chair. Now, in ImageNet, the common performance metrics are the top one score, so essentially checking if a sample's top class, so the one with highest probability, is actually the same as the target label, or top 5 score. So this is a bit more of a relaxed score. Check if your label is in your 5 first predictions. So you have a bit of a margin of error there. You can also have the top 5 errors, so the percentage of test samples for which the correct class was not in the top 5 predicted classes. Now, if you look now at this image here, this is kind of a famous image that shows the top 5 error on ImageNet. So we want to have it as low as possible. And you see the kind of solutions that were presented until 2011, which were non-CNN based, and how these solutions had a top 5 error of around 25. And how the first architecture, the first CNN solution that arrived in the field of computer vision and kind of made this surprise arrival by cutting the ImageNet error in half. And this was the AlexNet architecture in 2012. After that, 2013, 14, more architectures appeared, the error kept going down until it reached essentially human performance. So we now have CNNs which are sort of superhuman and can perform better than human in the ImageNet challenge. So let's see what this AlexNet architecture is. So this was published in 2012, so still not the newest architecture, but kind of revolutionized the field of computer vision by showing that CNNs were actually applicable and they were actually giving really good results, in this case cutting the ImageNet error in half. So AlexNet, unlike LeNet, worked directly with RGB images, so it had larger image, 227 by 227, and a depth of 3, so using the red, green, and blue channels. And what AlexNet did, mostly due to GPUs at the time not being large as they are now, is that it started with a pretty aggressive operation of spatial reduction. So you can see that we start from a 227 by 227 map, and we reduce it in the first step, in just one convolutional layer. We reduce it to 55 by 55. And this is because AlexNet uses pretty large filters, 11 by 11 filters, which are also not so common right now. And it uses stride of 4, which is also pretty aggressive. And again, this was just so that all this architecture could fit into memory and you could actually train this architecture. So nowadays, using a stride of 4 or such large filters is not really common practice. So as we add more layers to AlexNet, right? The first layer is the only one that has these really large filters. The other layers are like 5 by 5. They're max-pool operations of 3 by 3, so also a bit aggressive on that side. But in general, the only first extreme reduction is at the beginning. And it uses also same convolutions, so same as LeNet. And again, as with LeNet, what we're trying to get with these convolution operations and pooling is to reduce the width and the height, the spatial resolution, and to augment the depth of the activation maps that we're getting. So we started with a 227 by 227 by 3 representation and going all the way to a 13 by 13 by 256. Now after that, we had a series of other convolutions, small convolutions, 3 by 3, same convolutions that are kind of refining these features until we reach a representation of 6 by 6 by 256. Now after that, we need to map this representation into the number of classes of ImageNet. So again here, we're going to use a series of fully connected layers in order to shape these features into the number of actual outputs that we need to deal with that particular data set. And you can see here, look at the depth of all these filters. Again, these are the number of convolutions that you have in that particular convolution layer. So in the first operation, in the first convolution layer, I have a depth of 96, which means I have 96 11 by 11 filters, and they are applied with a stride of 4. So in the end, after all these fully connected layers, we have an output for 1,000 classes to work with ImageNet. So this is, of course, not as simple as the digit recognition that LeNet was targeting. So we need a larger network. And so we have this softmax for 1,000 classes at the end. So overall, AlexNet is similar to LeNet. It follows the same concept of convolution pooling, reducing width and height, and augmenting the depth, but it is much, much bigger. It's around 1,000 times bigger. And a key architectural design is that as nonlinearities, it uses rectified linear units instead of tonnage or sigmoids. And so this gives us a network that now has 60 million parameters. So we went from 60,000 parameters to 60 million parameters, which is really, really large. Therefore, of course, we need the data set to train these 60 million parameters. Like imagine using 100 images to train this model. This is completely unfeasible. So this is why ImageNet, that is very large, enable to use these large architectures to actually train them for the class of image classification and also to outperform all previous methods. So we now move on to VGGNet. And this appeared in 2015, so 3 years after AlexNet. And the whole idea of VGGNet was to simplify the architecture. So if we look again at AlexNet, you see that there's a lot of design choices that made AlexNet possible, right? So at first we choose filters of 11 by 11, we choose stride of 4, but then we have 5 by 5 same convolutions. Suddenly towards the end we have 3 by 3 same convolutions, and we have 3 convolution layers one after the other. We have 256 filters, 384 filters, 96 filters. I mean, these are all design choices, right? And the question is this necessary to make all these tiny changes? Is this the best architecture, right? I mean, maybe we don't need to change things so much. So this was the goal of VGGNet, to strive for simplicity and to decide 2 key design choices and keep repeating them throughout the architecture. The first choice is to have convolutions with only 3 by 3 filters, and all of them using stride of 1. And all of them are going to be same convolutions. The second design choice is to have max pool with 2 by 2 filters instead of 3 by 3 filters that AlexNet had with a stride of 2. And what this essentially does is it takes your map of 24 by 24 and it reduces it to 12 by 12, so reducing it by half. And so this is how VGGNet is constructed. So remember the key design choices that we have put here on the top right of the slide. And we start from our image 224 by 224 by 3, and we apply 64 convolutional filters. And we apply them twice, so hence the multiply by 2 here. These are same convolutions, hence we have an output of 224 by 224, spatial size doesn't change, and now we have 64 channels. Next operation is reducing the size with pooling, which brings us to 112 spatial size. Then we apply other convolutions. Now we're going to use more convolution filters so that the depth of our activation map is increased. So now we have double the number of filters, 128 is our depth. We apply pooling to reduce spatial size, and we keep repeating this operation, right? So we keep increasing the number of filters, so the depth is increased. We keep doing the pooling operations to reduce the spatial size until we reach this 7 by 7 by 512 representation. And on top of this representation, we put our fully connected layers and the final softmax for the 1000 classes. So again, this architecture follows the paradigm convolution pooling. As we go deeper, the width and the height, the spatial resolution is reduced and the depth is increasing. And there are several VGG architectures. You might hear names like VGG16, and this indicates the number of layers that have weights. So in VGG16, there are 16 layers that contain weights. And this architecture has now 138 million parameters, so more than double the parameters of AlexNet, deeper architecture, and therefore double the capacity to learn more about the ImageNet challenge. So it is a very large architecture, but the fact that it is so simple, that it contains just these operations that keep repeating themselves and you don't need to think about anything else, actually makes it very appealing. And also note that another decision that they made was to keep doubling the number of convolutional filters. So here they started with 64 filters and 128, 256, 512. So this was another key design choice. And so if now you want to make your VGG have 19 layers, you know exactly what you have to do in order to create it. So this simplicity actually makes it very appealing. But of course, nothing is so simple as we would like to believe. And lots of architectures were analyzed in the paper, and this was found to be actually the most effective. But this didn't happen at random. So they did try a lot of architectures and analyze what was the effect of these key design choices. So it is simple, but it doesn't mean that it's easy to arrive at this result. Good, so now we're switching to a very interesting concept in convolutional neural networks, and this is the concept of skip connections. So we have a problem actually if we want to keep adding more and more convolution layers. And that is the classic problem of depth, where training is starting to become harder. First of all, because we have vanishing and exploding gradients, that is that the gradients do not really arrive to the early layers of the neural network, and therefore we cannot train arbitrarily deep networks. So now the question is, if I create an architecture which has more layers, I'm going to have more expressive power. So I do want to explore this expressive power. I do want to have networks which have 100 layers, for example. What would happen if I could train a network with 100 layers? So this is the question that we're trying to answer, and we're trying to answer with residual blocks. So let's start with this example. We have here depicted two layers. This layer can have any shape, can be convolution, can be fully connected, doesn't really matter. The point is that we have two layers. So we have the input, which was the output of layer L-1, the output at layer L, and the output at layer L+1. And now we can see what happens inside these networks, right? We have all of these operations that are starting by the input at L-1, so the output of L-1, which is being the input of layer L. Therefore, it's multiplied by the weights of layer L, and we also take into account the bias. So this is the operation, the linear operation that happens inside layer L. Then we have a nonlinearity, which is placed on top of that. And for the next layer, we're going to have exactly the same operation. We're going to take the output of layer L, which is XL, and we're going to process it with the weights and biases of layer L+1. And this will give us the output XL+1. Again, remember that F is the nonlinearity that is applied on top of the linear operation. So this is the operation that is happening inside this block. Now, we have simplified these operations with this sketch here of this linear operation, nonlinearity, linear operation, nonlinearity, one happening after the other. And now in the forward path, of course, we have to go through all of these operations. So this is the main path of computation. We have to go through each of these operations. But what if I now say, you know, I want to skip some of these operations, and I want to create what is called a skip connection. So I want to be able to take the output of layer L-1, to take XL-1, and to bring it directly, to skip these two layers here, and to bring it directly to XL+1. Just copy-paste. So essentially what one can do is one can take the main path, which we depicted here. This is the last operation, the operation at layer L+1. And one can take this operation and add this skip connection. Therefore, simply add the input, which was XL-1. Simply add it there before the nonlinearity. So this is a skip connection. A connection between the input before it is processed by these two layers, which directly goes to the output, and we simply sum it up here. Again, this is before the nonlinearity. So now, in order for this operation to be valid, we need to make sure that the size at the output XL+1 is the same as the size at XL-1. Of course, if we have convolution operations in the middle, in these two layers in the middle, and these are heavily reducing the spatial size of the activation maps, then once we reach this point here, the two sizes will not be the same. So if we're using convolutions, we need to use same convolutions because we need the same dimensions. And otherwise, what we need to do is we need to convert the dimensions with a matrix of learned weights or with zero padding. So a bit more complex things, but it's important that the size of XL-1 is the same as the size of XL+1 so that we can sum up these two representations. So this is essentially a ResNet block, a block used to build residual networks. And so if a plain neural network consists of these two layers, so essentially a weight layer followed by nonlinearity, another weight layer followed by another nonlinearity, a residual block which creates this residual network would have, aside from this operation in the plane net, would also have this skip connection here. And this skip connection, what it does, it takes the input and copies it at the end, so kind of skipping these two weight layers. But a ResNet is, of course, really large, right? So we have all of these skip connections that are skipping all of these convolutions, different convolutions that perform different feature extractions. And then we add all of these skip connections in the middle. We put a bunch of clever design choices, and we get really good results with this network. And this is still one of the architectures that is most used in computer vision applications. In the case of ResNet 152, we went to 152 layers, so really deep neural network, but we still keep the number of parameters fairly small because we now have the same number of parameters as AlexNet had, which is 60 million parameters. So you might wonder now, how do these network actually train, and why do we need these skip connections? So the first observation that we need to make is, how about we take a normal neural network, which in this case they called plain neural network, and we train it, we augment the number of layers, we make it deeper and deeper and deeper, and we train these neural networks and we see what happens. So in this case, what we have in the x-axis is the evolution as we train the neural network, so the number of iterations, and in the y-axis we have the error. Now, of course, at the beginning of the training, what we want to observe is that our error is going down, and this is perfect. Another thing that we can observe is that with a 20-layer plain net, we have a lower error than with a 32-layer plain net, or with a 44-layer plain net, or with a 56-layer plain net. So this is already odd, right? Because what we're saying essentially here is that a 56-layer neural network performs worse than a 20-layer neural network, which essentially means that either the network is not training properly or the network is overfitting to our train set. So in this case, this is the case for plain nets. But if we move to ResNets, we see a completely different story. We see a story where the 20-layer neural network has a higher error than the 110-layer neural network, which means that making a plain network deeper and deeper and deeper is of no use. So at some point, we will not be able to train all this number of parameters. We will have vanishing gradient or exploding gradient, anything that doesn't allow us to surpass the performance of shallower networks. In the case of ResNet, this is the opposite. As we make the network deeper, we get consistently better results. And this is depicted here in this plot on the left. So another question is, why is that, right? Why do ResNet works? Why are these residual blocks so important? And why do they enable us to train deeper and deeper neural networks? So we look at this specific configuration in which we have a neural network depicted here by this box with NN, with any layers, and we add a residual block, just one residual block to this neural network. And we ask ourselves, how is this block really affecting my performance? So the operation that we compute in this block is depicted by these formulas, which we already talked about before. And remember that here we have the skip connection. We have this copy of the XL-1 output to skipping these two layers and going directly to the output XL+1. So now let's assume that these two values, for whatever reason, these two values are 0. The input is small, the weights are small, anything. But these two values lead essentially to 0 in this multiplication and also 0 on the bias. So all that we're left with is XL+1, which is a nonlinearity applied on top of the input, the initial input, XL-1. So we kept the same values, right? The residual block didn't do anything. We kept the same values, XL-1, but we added a bit of expressiveness to the network because we added the nonlinearity. So overall, with the skip connection, the identity, that is, having the same as output as we had as input, is really easy for the residual block to learn. We just have zeros here as an output, and then the residual block is essentially learning the identity plus nonlinearity. So it is guaranteed that this residual block will not hurt performance. It can only improve. Because if the weights of this neural network make it worse to have XL+1 as an output as XL-1, so basically these two layers are making everything worse, I can always set them to 0. The network can decide with gradient descent, with the training, to set them to 0 and to have the same output as the input that we had. And therefore, any performance that we have with this output, we're guaranteed to also have it with this output here, with the skip connection. So this is why we can guarantee that we can add as many residual blocks as we want, and the performance can only improve, but it cannot actually be worse as what we had before. Good, so residual networks are a milestone in, at least for computer vision, and these are very much used in all types of computer vision applications. So very powerful architecture. But let's move on now to another concept, and this is the concept of one-by-one convolutions. So you might wonder, what are one-by-one convolutions, right? I mean, we thought that the idea was to have a kernel, for example, this 3x3 kernel that took a patch of the image and aggregated the information into this one value, right? That applied some sort of filter on the image. And a one-by-one convolution doesn't really seem to do anything, right? So if this is a 3x3 convolution, we can define a one-by-one convolution by simply having a kernel which is 1x1. That is just one number. And of course, now this kernel is very easy to apply the kernel to our image. And since the kernel is 1x1, we actually don't need any padding, and we're guaranteed to have an output which is going to be, you guessed it, a 5x5 output. And this 5x5 output is nothing else than a scaled version of the input. That is, you take all the numbers that form this 5x5 image, and you multiply it by the weight of the 1x1 kernel. So you multiply by 2. So we're going to have all this matrix which is scaled with respect to the input. So the key things to remember about one-by-one convolution is that the dimensions of the input are kept also in the output, no need for padding, and we are getting a scaled version of the input. So let's look now at this example here. With a matrix with a depth of 1, this is not really interesting, right? Doesn't do anything for us. But let's look at what happens when I apply a one-by-one convolution to an RGB image, which is 32 by 32 by 3. So of course, what I need to do is I need to have the depth which is equal to the depth of the input. Right? So one-by-one convolution is not really about having one weight, but if I have a depth of 3, I'm going to have 3 weights which act directly on this depth of 3. So it is as though I would have 3 neurons put on top of this particular spatial location. And from these 3 neurons, I want to create one output. So it's the same as having a 3-neuron fully connected layer. Now, I'm going to have the same 3-neuron fully connected layer applied to all the spatial locations of the image, because this is still a convolution operation. So I'm going to slide my filter on top of my image. And from my 32 by 32 by 3 input, with one filter, which is going to be 1 by 1 by 3, so 3 weights, I'm going to obtain one output, which is going to be 32 by 32 by 1. So the only thing that I've changed here is I've scaled the numbers of my input, and I've essentially changed the depth of my matrix. So first I had an input of 32 by 32 by 3, and I've converted it into 32 by 32 by 1. Of course, if I create a convolution layer with 1 by 1 convolutions, I'm going to have more filters. I'm going to have, for example, 5 filters. And now I've turned my 32 by 32 by 3 representation into a 32 by 32 by 5, because I'm going to have 5 filters. And now you will wonder, why do we actually need this 1 by 1 convolution? They seem to be doing not much. So how can we actually use them? And it turns out that 1 by 1 convolutions are very much useful to shrink the number of channels. So let's imagine that we're dealing with this representation 32 by 32 by 200. So we have worked through our convolutions, but we have ended up in a cube, in a representation, which has too many channels. And so it's really, really expensive to now work on this representation. What we can do is we can first use 1 by 1 convolutions to shrink only the depth, but keeping the spatial resolution. And we can easily do this with 1 by 1 convolutions, which are going to act on the whole depth of the activation map. Therefore, they're going to have 200 weights, 1 by 1 by 200. And if we use 32 filters, then we're going to have an output of 32 by 32 by 32. So really an easy way to shrink the number of channels, adding a nonlinearity, therefore a bit of expressiveness power, and reducing the multiplications that we do after this operation. So the addition of a nonlinearity is always good, right? One can learn more complex functions, but again, the goal here is to reduce the number of channels so that the subsequent operations are cheaper. And this is one of the key concepts that is going to make the inception layer work in practice. So what is the inception layer? Now, the motivation for having an inception layer is so that we don't have to choose filter sizes anymore. So do I choose a 3 by 3 filter or a 5 by 5 filter, even 7 by 7 filter? I mean, which one is better? Do I have to go through each layer and try all possible combinations? So why not using all the filters at the same time for a particular layer? So I have a layer and I don't have to choose to use only 3 by 3 filters or only 5 by 5 filters, but I'm going to use them all. Of course, this is incredibly expensive, right? Because I have the output of my previous layer, and I now have to compute 1 by 1 convolutions, 3 by 3 convolutions, 5 by 5 convolutions, and a further pooling operation. I'm going to perform each of these operations in parallel, and then I'm going to merge the results of all of these operations. So then my next layer can use this improved feature extraction power that comes from having different filter sizes. So how can this work in practice? So first of all, we're going to have only same convolutions, right? Of course, the sizes would not match. You would have to start doing weird operations. So if we use same convolutions, we know that the output spatial size is going to be the same for all of the operations. And for the 3 by 3 max pooling, we're going to have a stride of 1. So let's look at possible sizes that we could have if we work with such an inception layer. So let's say we start with the previous layer. We get an output of 28 by 28 by 192. So we have quite a lot of depth already. Now imagine that the 1 by 1 convolutions, the 3 by 3 convolutions, the 5 by 5 convolution, and the max pooling all have to work with a depth of 192. So the 1 by 1 convolutions are going to have, for one filter, 192 weights. For the 3 by 3 convolutions, 3 by 3 by 192, and then multiply by the number of filters. 64 in the case of 1 by 1 convolution, 128 in the case of the 3 by 3 convolution, and 32 in the case of 5 by 5 convolution. So these are a lot of multiplications that are happening because the previous layer has quite a large depth. Now, furthermore, once we have performed the 1 by 1 convolutions, the 3 by 3 convolutions, 5 by 5 convolutions, and the max pooling, we need to take all of these results and we need to concatenate all of these filters. So we take all of these representations and we concatenate them in the number of channels, which means that we will end up with a representation which is 28 by 28 by 416. So from one layer to the next, we have gone from 192 to 416. So of course, this is absolutely not sustainable. We put a couple of layers, a couple of inception layers, one after the other, and suddenly the number of parameters, the number of multiplications has really blown out of proportion. So what can we actually do to keep these operations manageable and the number of multiplications manageable? And here we have 1 by 1 convolutions to the rescue. So let's look first at the computational cost of having a 5 by 5 convolution operation on top of a 32 by 32 by 200 activation map. Let's assume that we want to apply 92 of those filters, so we want to get in the end our presentation, which is 32 by 32 by 92. Now, first of all, we have to realize that our filters are going to be 5 by 5 by 200 because the depth of our input is 200. So we're going to have, for one filter and one position, one spatial location, we're going to have 5 by 5 by 200 multiplications, just for placing the filter in one position of our input. Now, of course, this is just one value of the output volume, right? Only one of the 32 by 32 by 92. There's only one value being created with this number of multiplications. So now we have to multiply it by the actual output volume in order to recreate the values for all of the output. So in order to perform this operation and obtain values for the 32 by 32 by 92 activation map, I need to do roughly 470 million operations, right? Crazy that I need to do all these operations for just one convolution operation, just the 5 by 5. Then I'm going to have the 3 by 3, I'm going to have the 1 by 1, I'm going to have the other layers. This is too much. So what I'm going to do is I'm going to play around a little bit with 1 by 1 convolution. And so what I say here is, what if before applying the 92 filters, the 92 5 by 5 convolutions, I actually apply a 1 by 1 convolution? And the only goal of the 1 by 1 convolution is to reduce the depth of my activation map. So I'm going to apply 16 filters. So the depth is going to be reduced from 200 to 16, and then I'm going to apply my 5 by 5 convolution. Note that the input and the output sizes are exactly the same. So let's look at the computational cost of this alternative architecture. Well, the number of operations for the first convolution layer is going to be, for each 1 by 1 filter, I'm going to have 200 multiplications. And this is to create one value of the 32 by 32 by 16 output. Therefore, I need to multiply it by these three quantities in order to create all the multiplications that I need to go from a 32 by 32 by 200 activation map to a 32 by 32 by 16 map. Now, the second operation now, what happens is that my 5 by 5 convolutions are now 5 by 5 by 16 because the depth of my input is not 200 but 16. I'm working here with the middle representation. So I'm going to have, for one location of my output, I'm going to have 5 by 5 by 16 operations, much less than before. And therefore, these are the total number of operations that I need to do in order to create my output of 32 by 32 by 92. So in total, all of these operations put together are 40 million multiplications. So we went from 470 million multiplications to around 40 million multiplications. So we have reduced the number of multiplications by a lot by using this 1 by 1 convolution in the middle. And note that I have not changed the output size. So I'm still going to have my 32 by 32 by 92 output, and I'm still going to apply 5 by 5 convolutions. So with this 1 by 1 convolution, very simple operation, I can reduce the number of multiplications, in this particular case by 1/10. So this is what the Inception layer uses to keep the number of multiplications and the depth of the representations in a manageable number. So I'm going to place these yellow blocks, which are 1 by 1 convolutions, before the convolution operations, especially before the 3 by 3 and the 5 by 5 convolution, and also after the max pooling. So let's see the example with the sizes that we had before, but now what happens with these 1 by 1 convolutions. So I'm going to have my previous layer, which is still 28 by 28 by 192. And I'm going to keep 1 by 1 convolutions exactly the same. So since 1 by 1 convolutions are small, I can actually handle this 192 weights for each filter. So I'm going to keep this the same. But I'm going to place 1x1 convolutions in front of the 3x3 and the 5x5 convolutions. And what this essentially do is they reduce the size, the depth of my representation from a 28 by 28 by 192 to a 28 by 28 by 96. This means that the 3x3 convolution now will have much less multiplications because they will act on a depth of 96. Since the 5x5 convolutions are even more expensive, I'm going to reduce the size even more and work on a representation of 28 by 28 by 16. And now the max pooling, right? So why do I have a 1x1 convolution on top, so after the max pooling operation? Well, we're looking at the output of all the other representations. The 1x1 convolutions have 64 channels as output, the 3x3 convolutions have 128 channels as output, and the 5x5 convolutions have 32 channels as output. If I keep the 192 channels of the max pooling, then the max pooling will have an overwhelming representation of the output. And we don't really want that. So we really want to give a lot of weight to the convolutions, which are actually the feature extraction units. This is why I'm going to reduce the number of channels that max pooling uses to 32. And I'm going to do this exactly with 1x1 convolutions. So I've achieved two things here. I have reduced the number of multiplications, but I've also reduced the output size, which is now 28 by 28 by 256. And this 256 comes from nothing else than taking the 64 channels of 1x1 convolutions, the 128 channels of 3x3 convolutions, 32 channels for 5x5 convolutions, and finally 32 channels for the max pooling operation. So if I sum up all of these channels, I obtain the 256 channels that I'm going to have as output. And this inception layer is of course, putting one layer after the other is what creates what we know as GoogleNet architecture. So we have here represented one inception block, which is the block that we were discussing with the 1x1 convolutions and the 3x3, 5x5 convolutions and max pooling, and all of these operations put together form an inception block, which is just a little piece of the GoogleNet architecture. Now, of course, in the middle, I'm going to have some extra max pooling layers because with the max pool operation using a stride of 1, we have not really reduced the spatial size of the activation map. And therefore, we're going to place certain max pool layers also in the middle to actually reduce the spatial size, to still follow this idea that started in LeNet of having convolution pooling, and reducing the width and height of the representation and increasing the number of channels. The last architecture that I want to talk about today is the exception net. And this is because it has a special type of convolutions that are really interesting and that have a similar goal as the 1x1 convolutions in Inception net. And these are depth-wise separable convolutions. So what are these? So this is a representation of a normal convolution, right? A normal convolution acts on all channels. So as we have been saying since the last lecture, the depth of the filter is going to match the depth of the input. In this case, I have a 5x5 filter, and the depth of the filter is 3 because the depth of the input is also 3. And again, I apply this convolution, I obtain 256 channels, which means that I have 256 of these filters being applied to the input. So these are normal convolutions. With depth-wise separable convolutions, what I have is that I have a filter which is specifically applied only for certain depth of my input feature map. So in this case, if I have a depth of 3, I can have, for example, 3 filters, the orange, the red, and the yellow, each of them is applied to one particular channel of the input. And that filter is only going to be applied on that channel. And here you can see how you can actually code this in PyTorch, and normal convolutions actually have this value which is called groups set to 1, which means they're acting on all the depth of the input, while the depth-wise separable convolutions that I used in this particular example have groups set to 3. And this gives us an output which is now going to have depth of 3 also, because each of the filters, each of the orange, red, and yellow filters is going to give us one of these 8x8 representations of, as output. So the depth is not really changing because I have 3 different filters, and therefore the depth of the output is also 3 for this particular configuration. So this is really important to see the difference between depth-wise separable convolutions, where do they act on, where the multiplication is happening, but also how does this change the output size. So now I applied this, this depth-wise separable convolution, and so now I have an output which is 8x8x3. But I didn't want to have this output in the first place, right? I want that my convolution operation has an output of 1. And then if I apply 10 filters, now my depth is going to be 10. So what do I do really with this output, which has now depth 3? Well, the solution here again are 1x1 convolution. So I first perform my depth-wise separable convolution, and I then use a filter of 1x1x3 in order to reduce, to change the depth of my representation to be only 1. So with these 2 operations, I can mimic what a normal convolution is doing. One filter of 5x5x3, normal convolution, is giving me a representation of 8x8x1, and now I can mimic these input and output sizes by having a depth-wise separable convolution plus a 1x1 convolution. But the question is, why do I want to do all of this, right? Why do I want to use depth-wise separable convolutions if in the end I want to have a representation which is 8x8x256? So again, let's look at the number of multiplications. With this normal convolution operation with a filter of 5x5x3 and 256 of these kernels, I'm going to have more than 1 million multiplications just for this particular convolutional layer. Let's look at what happens with depth-wise separable convolutions. For the depth-wise convolution, I'm going to have 3 kernels of 5x5x1. And so I'm going to have 4,800 multiplications only for this operation here. But I also need to do the 1x1 convolution. So I need to sum up the number of multiplications that the 1x1 convolution does in order to reduce again the size to 8x8x1. And if I now multiply it by 256, which are the number of kernels that I want to have in order to have an output of 8x8x256, I end up at 49,000 multiplications. Still, the summation between 4,800 and 49,000 multiplications is much, much less than the initial more than 1 million multiplications I needed, and my input and output are exactly the same. So basically, with depth-wise convolutions plus 1x1 convolutions, I can reduce heavily the number of multiplications. And this is what ExceptionNet uses in order to further reduce the number of multiplications. So a slightly different concept than the one in InceptionNet, but still with the goal of reducing computation. So after seeing all of these architectures, we go back to the ImageNet challenge. And we see here the evolution of the ImageNet classification top 5 error. So here, of course, the smaller the better. And we see how we started with AlexNet, 8 layers. This architecture already reduced the error by quite a lot compared to non-CNN methods. Then we had VGG with 19 layers, lowering the error even more, GoogleNet, Inception, but the real revolution came with the depth, came with ResNet that could really push the number of layers from 36 to 152 layers, so crazy amount of layers, and further push the error to be lower, to be 3.57%. So there is really a big revolution, especially in growing neural networks with the residual blocks. So the last concept, the last type of architecture that I want to discuss today is the fully convolutional network. So we have seen the classic structure for a classification network. This is the structure where we have a series of convolutions that act as a feature extraction, and then the fully connected layers, right? So starting from LeNet, going to AlexNet, we had always these last fully connected layers that took the activation map, the feature map, from the convolutional layers and turned it into a classification result. For example, there is a cat in this image. And there was always this set of fully connected layers. Now, what if I could actually convert the fully connected layers also to convolutional layers? Now, it turns out that, as we have seen, one-by-one convolutions are exactly the same as fully connected layers. So one could easily replace fully connected layers by one-by-one convolution. And with exactly the same operations, we would be having a network that is now fully convolutional, simply by replacing fully connected layers with the equivalent one-by-one convolution. Now, the cool thing about this is that if I have a larger image, and these three last layers would still be fully connected layers, I cannot really work with this larger image. So remember that whenever you have fully connected layers, the size of your input is completely fixed, because the fully connected layer is always going to take the same number of inputs. With a fully convolutional layer, things change. So now if I have a small image, it can be that here I end up having this one-by-one representation. So the spatial size has been reduced to one-by-one. But if I now take my image and I make it bigger, I can still work with it because all my last operations are not fully connected, but are now convolutional layers. And therefore, as a convolutional layers, I can slide my filter on any image size and I can still work on it. And the only thing that is going to happen is that my final representation might not have a size of 1 by 1 by the number of channels, but now has a size of h divided by 32 multiplied by width divided by 32 and the number of channels as depth. But I can still work with this representation. So having a fully convolutional network is useful because I can work with any image size. Now this, of course, might not sound so fancy if we want to perform image classification. But what if we actually want to have an output which has the same size as the input? For example, we want to perform semantic segmentation, in which for each pixel in the input, we want to assign a semantic label. For example, cat, dog, sofa, etc. In this case, what we would want as output is to have a representation with spatial dimensions h times w. And therefore, we need to work absolutely with fully convolutional architectures. Now, of course, the key in semantic segmentation is going from this tiny representation, which has this small spatial size due to the convolutions and poolings that we have performed, to a size that is now the same as the original image. Hence, how do we perform this upsampling? How do we go back to the input size? So there are several ways to do this. The easiest way is through interpolation. So we start with our small representation, and what we want to do is we want to double up the size. Now, of course, we can take the original values, which are depicted here in this blue-green color, and we can spread them throughout the map. But still, we're going to have places in which we don't really know what kind of value to put. We don't have more values to put in there. So what we can do is we can use common interpolation techniques, nearest neighbor interpolation, bilinear interpolation, or bicubic interpolation. In the case of nearest neighbor interpolation, what you do is you land on a pixel that has no value, and you look at what is the value of the nearest neighbor with an actual value from the input image. This is why you have this kind of effect where you have all of these squares with exactly the same value. These are all the squares for which the nearest neighbor was the same, and therefore they copied the value of the nearest neighbor. You also have bilinear interpolation, in which you look at different neighbors, and depending on how far they are, you essentially perform a weighted average of the pixel. Therefore, you have this blurry effect, but a bit more natural. Or you have the bicubic interpolation, which is yet another way of gathering information from neighbors. So the cool thing about interpolation is that you introduce few artifacts, especially with bilinear interpolation. You just blur the image out, and therefore you can continue processing this representation. The other way of doing things is with transposed convolutions, which is essentially taking your representation, blowing it up, same thing as we did before, therefore taking these blue-green values and spreading them throughout the map, and then processing this representation with a series of convolutions. So there is always this upsampling plus convolution operation. So it's very efficient, and you also have the advantage that you have the convolutions after the upsampling, which help you refine your representation. Now, the transposed convolution, as I said, revolves around these two operations. The operation of unpooling, which take your representation, which was here in blue. You had this 3x3 representation, therefore 9 numbers. It performs unpooling, which is the opposite operation of pooling. But of course, then this representation is not enough. You have a lot of blank spaces for which you don't have any values. So you fill all of these values with 0, and then you put a convolution filter on top, which is now going to fill these values with a convolution operation. Now, this operation is also called up convolution, so transpose convolution, up convolution, but not deconvolution. That is completely another type of operation. This is, so the transpose convolution or the up convolution is this operation of unpooling plus having a convolution filter which is learned just like all the other convolution filters through backpropagation. And this is not the case for deconvolution. Now, if one does a cascade of these unpooling plus convolution operations, so cascading transpose convolutions and upsampling the representations to a larger and larger, then we get what is called an encoder-decoder architecture. And we also had, if we further add skip connections, the UNet architecture. So we can take a look at this UNet architecture very briefly. What does it mean? So on the left side of this U shape, so starting from this representation and going all the way down, we have the classic convolutional neural network architecture, which revolves around a series of convolutional filters plus pooling operation. So feature extraction plus feature selection. So you can see how after each of these convolution layers, you have a reduction in spatial size, and this is due to the pooling operation, which is represented by these red arrows here. So the blue arrows that go to the right, point to the right, are convolution operation. The red arrows are max pooling operations. And once we reach this bottleneck representation is when you have the smallest spatial representation in your UNet. Your goal is to upscale this representation again to have the same output size as we had in the input. And we do this with up convolutions, with these green arrows here, which do unpooling plus a series of convolution. So you can see here how we are doing the up convolution, then we're processing it with further convolutions. We're doing up convolution following with a series of convolution operations. Now, the extra thing about UNet, so this is a classic encoder-decoder architecture, right? We have the encoder here on the left, and we have the decoder here on the right. So encoder shrinks the spatial size, decoder blows it up. But the cool thing about UNet are these gray arrows here in the middle. These are called the skip connections. And these have a very similar function to the skip connections in ResNet, right? They will remind you to the skip connections in ResNet. And what they do is they take this representation here, the representation of the encoder, and they copy it over to the decoder. Now, the idea here is that during the convolution and pooling operations of the encoder, you might have lost some spatial resolution, right? There is a lot of expressiveness power in these operations. You condense the information, so you have really high-level information in your bottleneck, but you're losing detail, you're losing spatial detail. So if you want a segmentation map as output, this is a pixel-wise output, and it has to be pixel precise. Therefore, we cannot afford to lose so much spatial resolution. And this is why you have these skip connections that copy the feature representation all the way to the decoder, so the decoder also has access to those large spatial maps. And you can put skip connections at any level that you want. So to summarize, a UNet has two parts. The encoder, which is the contraction part, which captures the context of the image with this series of convolution and pooling operations. You have, of course, your 3x3 convolutions in the case of UNet, you have your relu activation, and then you have your max pool operation. Now, the height and width of your representation is going to go down, same as for LeNet, and the depth is going to increase. In the decoder, the opposite is happening. The height and width are increasing, while the depth is decreasing. And so you have this 2x2 up convolution that is going to halve the number of input channels. You're going to have the skip connections that are going to concatenate the feature map from the encoder and the feature map from the decoder. And then these representations are going to be processed by normal 3x3 convolution. And finally, of course, what you want is to have a map which is h times w times the number of classes. So for each pixel, you want to have a semantic representation. And in this case, we have 64 channels, we have 64 classes, so we can assign to each pixel one of these 64 semantic classes. And you do this with a final 1x1 convolution. With this, we reach the end of the lecture. Thank you for your attention and see you next time.